Hello students, welcome back to the series Coordination Chemistry. This is the 6th module of the series, Theories of Coordination Compounds. In the previous classes, we have already discussed two of the preliminary theories in coordination chemistry, that is Werner's coordination theory and Sidgwick's concept of coordination. And now we are moving to one of the modern theories of coordination compound, that is valence bond theory. And now the modern theories, in addition to valence bond theory, we have other two theories also, that is crystal field theory and molecular orbital theory. All these three theories are the most modern theories of coordination compounds. And this VBT was proposed by Linus Pauling and Slater in 1935. It was the first successful theory regarding the bonding of complexes. Bonding, the preliminary theories where they failed to explain the bonding of complexes, but this is the first theory to put forward to explain the bonding in complexes. It says that hybridization of atomic orbitals occurs before bonding. So, the concept of hybridization starts here. So, valence bond theory states that hybridization of atomic orbitals occurs before bonding. And now we have different postulates for this valence bond theory. Number one is central metal ion makes use its empty orbitals like Ns, Np, Nd or N-1d, Ns, Np for the complex formation with the ligands. The number of these empty orbitals is equal to the number of incoming ligands, that is the coordination number. So, first postulate is the central metal atom, it uses its orbitals, empty orbitals. It may be Ns, Np or Nd, Ns, Np and Nd or N-1d, Ns, Np. And they will be forming, and these orbitals will be used by the central metal atom and they will undergo hybridization, and these hybrid orbitals will be combining with the ligands. So, the number of these empty orbitals will be equal to the number of incoming ligands. It depends on number of incoming ligands. The empty orbitals that the central metal atom makes available will be depending on the coordination number of the complex. And second postulate is the metal d orbitals undergo hybridization to form equal number of new orbitals of equivalent energy. The concept of hybridization is, you may be familiar with the concept in the previous classes or preliminary classes, very small classes, from there itself you are studying hybridization. The same thing is here. Metal there in this case you have metal d orbitals, that is only difference. So, the number of hybrid orbitals formed will be equal to the number of orbitals that take part in hybridization, and all these hybrid orbitals will be having equivalent energy, that is same energy, and they are directed towards the incoming ligands according to the geometry of complexes. It will be depending on the geometry of complexes. The orientation of this hybrid orbitals will be according to the geometry of the complexes. And the hybridized orbitals have the maximum overlapping nature. These hybrid orbitals, after hybridization, the orbitals are called hybrid orbitals. The nature of that orbitals is they have the maximum overlapping nature. And now, the inner N-1d or outer Nd orbitals can participate in hybridization. The metal d orbital can use its inner d orbital or outer d orbital. And now we have next postulate is each ligand should contain at least one orbital with lone pair of electron. So, each ligand should contain at least one orbital with lone pair of electron, and this filled ligand orbitals can overlap with the empty hybrid orbitals of the metal to form metal ligand coordinate bond. We know that the bond, the nature of the bond is coordinate bond in coordination compounds, and this coordinate bond is formed by metal and ligand, metal orbitals and ligand orbitals. They will be combining to form metal ligand coordinate bond. In addition to the sigma bond, there is a possibility of pi bond formation also, and that will be depending upon whether the orbitals, suitable orbitals are there available on the metal atoms and ligand. So, in addition to sigma bond, pi bond formation is also possible in coordination compounds. This is the way the metal and the ligand orbitals combining to form the coordinate bond. We can see that metal vacant metal hybrid orbital is there. See this? This is the hybrid orbital, that is the orbital which is formed after hybridization. Such orbitals are called hybrid orbitals. So, hybrid orbitals of the metal is this. This is the ligand orbitals which is having a lone pair of electron pair. This should be donated to the metal, and they will be combining to form the coordinate covalent bond. So, metal ligand coordinate bond is formed. This is the way of forming that bond. And now, we have different geometries for the complexes. So, the common geometries are 4 and 6. I have already discussed all these possibilities of this coordination number. And for if the complexes is having the coordination number 4, this the possibility of two types, there is a two possibilities for forming this coordination number 4, that is one geometry is a tetrahedral geometry and second is a square planar geometry, and this is very well explained by the valence bond theory. How it is explained we will be discussing. First, in the case of tetrahedral complexes, means the complex is having a tetrahedral geometry. See the figure, you can see that there is a figure of a tetrahedral complex. The complex is having a central metal atom which is at the center of that cube, and to the central metal atom 4 ligands are being attached. See the arrangement of ligands, it forms a tetrahedral geometry. All the ligands are at the 4 corners of a regular tetrahedron. And now this TD structure is common with the metals with the D0 or D10 electronic configuration. D0 means 0, no electrons in the d orbitals, or D10 means 10 electrons in the d orbitals. So, this type of structure is common with the D0 or D10 electronic configuration. And normally this tetrahedral complexes show sp3 hybridization. sp3. sp3 means, you may be familiar with the hybridization, different hybridization sp, sp3, sp2 etc. means one s orbital will be combining with 3 p orbital to form 4 sp3 hybrid orbitals. So, tetrahedral complexes will be having an sp3 hybridization. See the example of a complex, that is tetrachloronickelate 2 ion, that is NiCl 4 times 2 minus. In this case, we have the central metal atom nickel. Nickel is a central metal atom. You can calculate the oxidation state of nickel, that is Ni2 plus. And before that, nickel atom is having an atomic number 28. 28 is the atomic number of nickel. So, the arrangement is, it is 4s2 3d8. 4s2 3d8. See this, you can see 2 electrons in the 4s orbital and 8 electrons in the 3d orbital. You can count 1, 2, 3, 4, 5, 6, 7, 8. So, 3d8 and 4s2 is a electronic configuration of nickel atom. And now, in the complex, nickel is having an oxidation state of 2 plus, Ni2 plus, which means that 2 electrons have been gone from nickel. And from where will it go? From where these 2 electrons will go? It will be going from 4s. And thus, Ni2 plus ion is having this electronic configuration, that is 3d8. It is remaining as such, but 2 electrons from 4s will be going. Okay. And now, this is the case. Now, according to the valence bond theory, depending on the number of ligands available, the central metal atom should make the empty orbitals for bond formation, right. So, how many ligands are there? There are 4 ligands, 4 chloride ligands. So, 4 orbitals should be there. And before the bond formation, the metal orbitals will be undergoing hybridization. So, the empty orbitals, how many empty orbitals are there? 1, 2, 3, 4. all others are 3 of them are completely filled, 2 are partially filled. So, the empty orbitals available are 1, 2, 3, 4. 4 orbitals, that is S1 s orbital and 3 p orbitals forming sp3 hybridization. So, the hybridization in this case is sp3, right? And how many sp3 hybrid orbitals will be formed? You know that when one s orbital is combining with 3 p orbital, it forms sp3 hybridization. So, on total you have 4 sp3 hybrid orbitals, and this sp3 hybrid orbitals will be taking the geometry, tetrahedral geometry, that is they will be orienting towards the corners of a regular tetrahedron. So, these sp3 4 sp3 hybrid orbitals will be available and they will be oriented towards the 4 corners of an octahedron. And now here comes the this chloride ions. Chloride ions will be coming and they will be forming bond with this nickel, this empty hybrid orbitals of nickel, and this 1, 2, 3 and 4 chloride ions will be forming metal ligand coordinate bond. This is the case. And now you can see that this cross, these electrons are donated by the ligands 1, 2, 3, 4, 4 chloride ions, 1, 2, 3, 4. Each ligand will be sharing 2 electrons. So, 1, 2, 3, 4, 5, 6, 7, 8 electrons will be gained by the nickel from the chloride ions. And now, let us have a look at the paramagnetic nature. What is the magnetic property of the complex? If we see the complex, you can see how many unpaired electrons are there in the complex. There are 2 unpaired electrons. See this, the complex, 2 unpaired electrons are there. Then we can say that the complex is paramagnetic in nature, and the magnetic moment, it is around 2 unpaired electrons means 2.8 something Bohr magneton, that will be the value of magnetic moment value. And this is the case of tetrachloronickelate ion. This is the way the valence bond theory explains the structure of this NiCl4 times 2 minus. And now coming to the next example, MnCl4 times 2 minus, another complex. We have manganese as the central metal atom with an oxidation state of +2. Again, manganese is 3d5 4s2, 3d5 4s2. And now for Mn2 plus, the 2 electrons will be, since Mn is 3d5 4s2. When it is Mn2 plus, these 2 electrons will be removed from 4s. And now after the removal of electrons, what will be the electronic configuration of Mn2 plus? It is simply 3d5. That is written there. That is all the 3d orbitals, they are all degenerate. That is why all is written like this. And how many d electrons are there? 5 d electrons, 1, 2, 3, 4 and 5. And now how many this ligands are there? 4 ligands. So, 4 empty orbital hybridized orbitals are to be provided by this manganese, and empty orbitals are 4s and 3 4p orbitals. So, sp3 hybridization, 1s and 3 p orbitals combine to form 4 sp3 hybrid orbitals, and 4 sp3 hybrid orbitals will be oriented towards the 4 corners of an tetrahedron, and this chloride ions will be coming and forming metal ligand coordinate bond. That is why this is the way of forming the complex. And now look at the magnetic behavior of the complex. It is having a paramagnetic nature because we have 5 unpaired electrons in the complex. So, highly paramagnetic, right? They are having magnetic moment is, the value is very high, because 5 means around 6, the Bohr the magnetic moment value will be around 6, 5.8 something will be the magnetic moment value. Okay. And this is the way of explaining. And now let us have a look at another example. It is the other example is NiCO4 times nickel tetracarbonyl, NiCO4 times. This is the complex. And now you have to identify the central metal atom. It is nickel. Nickel is having an oxidation state. Before that, you have to look at the ligands. It is having a charge. Carbonyl ligands are having 0 charge. So, nickel in the 0 oxidation state. Nickel is having an oxidation state of electronic configuration of 3D8 4s2. 3D8 4s2. That is shown in this in this figure. That is 3D8 4s2. And now in the electronic configuration, while we are moving to the when carbonyl ligands are approaching this nickel, the central metal atom nickel, you can see that this carbonyl ligands are having strong ligands. They are having the capacity to pair the electrons. They will be having the capacity to pair the electrons. How this pairing of electron take place? See this. There are 2 electrons in the s orbital, right? 4s orbital, there are 2 electrons. They will be coming here. One will be coming here and this get paired, and another will be coming here, that also get paired. Like this, the arrangement will be obtained, right? Again I repeat, we have the central metal atom nickel. Nickel with an oxidation state, that is 0 oxidation state, that is 3D8 4s2, which means that no electrons are given by the nickel. And now when carbonyl ligands are approaching, these carbonyl ligands have a high ability to pair the electrons in nickel. So, they will be pairing in the electrons, that is 4s2 will be coming here, and see this, one electron will be coming here, another electron will be coming here. Now, all the 3D orbital, it is completely filled, and the available s and p orbitals are there. Now, it will be undergoing sp3 hybridization. Why sp3 hybridization? We have 4 ligands coming near to the nickel, and 4 hybrid orbitals should be made available. Central metal atom should give 4 hybrid orbitals to the ligands, and so 4 sp3 hybrid orbitals are given. They will be oriented towards the 4 corners of a tetrahedron, and this is like this tetrahedral structure with sp3 hybridization. Now coming to the to explain the magnetic property of the complex. What is the magnetic property? It is diamagnetic, because no unpaired electrons are there. How it becomes diamagnetic? If you look at the structure of the complex, there is no unpaired electron. All the electrons are paired. So, we can say the complex is diamagnetic. That is, we have the mu value, that is mu equal to 0. Mu value will be 0 in this case. And now, this is all about tetrahedral complex. The coordination number 4, we have 2 possibilities, tetrahedral and square planar, and second type is square planar complexes. See, this is a square planar structure given, you can see there. In the square planar geometry, the central metal atom is at the center of a square plane, and the ligands are at the 4 corners of that square. The central metal atom at the center of the square, and 4 ligands at the 4 corners of the planar square. And this geometry is common with the D8 transition metal complexes, that is the transition metal complexes which are having D8 electronic configuration. And here the hybridization is DsP2. In tetrahedral complexes, the hybridization is mostly sp3 hybridization, but in the square planar complexes we have DsP2 hybridization. Example for a square planar complex is nickel tetracyanonickelate, means NiCN 4 times 2 minus. See how NiCN 4 times 2 minus complex is formed. According to valence bond theory, nickel atom is 3D8 4s2, that is known. Okay. Nickel is 3D8 4s2, it is shown there in the first figure, in the first row you can see. And in the complex NiCN 4 times 2 minus, nickel is with the Ni2 plus, 2 plus oxidation state. So, 2 electrons are gone from 4s orbital. So, that is the Ni2. From 4s orbital, these 2 electrons will be removed, and finally you get for Ni2 plus, it is electronic configuration is, it is like this 3D8 only. And now we have to look at how many this ligands are there. We have 4 ligands approaching the nickel. So, 4 ligands means 4 empty hybridized orbitals should be provided by the central metal atom nickel. And now this cyano ligands, cyano means Cn minus ligands, they are also very strong ligand. They are also having the capacity to pair the electrons, and this pairing of electrons takes place since these 2 electrons are unpaired electrons, right. So, this will be paired here and we will get a pairing with the empty orbital here. So, one d orbital will be empty by the influence of this cyano ligands. And now one d orbital is available, one s orbital is available, and 2 4p orbital should be needed, right. How many hybridized orbitals are to be provided? 4. So, we need only 1d, 1s and 2p. So, that is why dsp2 hybridization. This p orbital is not taken for hybridization because already we got an empty orbital from the d orbital. dsp2 hybridization. This is the way of forming NiCN 4 times 2 minus. And now you can comment on the magnetic property of the complex. See how many unpaired electrons are there? No unpaired electrons are there in the complex. Are there any unpaired electrons? No, no unpaired electrons. All the electrons are paired. So, the magnetic moment mu equal to 0 in this case, or we can say that the complex is diamagnetic. And also you may be, I think that you may be knowing this cross, these are the electrons, these are the electrons donated by the ligands. To differentiate between the metal electrons and the ligand electrons, it is denoted in a different manner only. These are all electrons only. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are provided by the cyanide ligands. Hope it is clear. And next example is CuNH3 4 times 2 plus. Here there is some kind of difference. See, you have the central metal atom copper with an oxidation state of Cu2 plus copper, and now copper is having an electronic configuration of 4s2 3d9, 4s2 3d9, and this 4s2 3d9, this is also Cu2 plus 4s2 copper 2 plus, because 2 electrons have been gone from 4s, and that is why it is vacant here. Actually, the copper is having the electronic configuration, the metal copper is having the electronic configuration 4s2 3d9. So, 2 electrons will be there. For Cu2 plus 2 electrons will be gone, and this Cu2 plus electronic configuration is written here. And now Cu2 plus in the environment of ammonia, when ammonia ligands are approaching this copper 2 plus ion, what will happen? This ammonia is also having the strength is higher. They are also capable of pairing electrons. So, how to pair? No electrons are to pair. What will happen? This ammonia ligand will shift this electrons to the p orbital. This pz, one of the p orbital, it will be giving electron. And now how many d orbitals are available for this hybridization? 1, 2, 3, 4. How many are needed? Only 4. So, dsp2 hybridization. Here also dsp2 hybridization occurs. And also, what about the magnetic moment of, or the magnetic property of the complex is also, it is also diamagnetic, because it is a paramagnetic complex because there is one unpaired electron in the complex. If the unpaired electron is there, you will call it as a paramagnetic, and if there are no unpaired electrons, it is diamagnetic. And now the second type of complexes, usually we have two coordination number, coordination number 4 and coordination number 6. 4 was discussed, that is square planar and tetrahedral complexes. And now moving to the coordination number 6, that is octahedral complex. You can see a regular the structure of a regular octahedron there. There is a central metal atom at the center and all the ligands which is marked in the green, they are all ligands, 6 ligands will be there. And now in the octahedral geometry, the central metal atom is at the center of a regular octahedron and the ligands are at the corners of an octahedron. Here the hybridization will be maybe 2 type of hybridization, that is it can be either sp3d2 or d2sp3. In the octahedral complexes, it can be either sp3d2 or d2sp3. And now you can explain the according to valence bond theory, different geometries of the octahedral complexes are explained. For example, CONH3 6 times 3 plus. Here also you can see the cobalt atom is having, it is a central metal atom, cobalt is having an oxidation state of 3 plus, and now cobalt 3 plus means it is having, cobalt is having an electronic configuration of 4s2 3d7, 4s2 3d7. If it is cobalt 3 plus, 3 electrons are to be given by cobalt. 3 electrons are to be given means 2 from the 4s orbital and 1 from the 3d orbital. So, on total the CO3 plus will be having 6 electrons in the d orbital. So, 6 electrons in the d orbital and no electrons in s orbital will be there. And now, what about the hybridization? See, you can see that this ammonia ligand is a strong field ligand, I have already discussed, and this is a strong, since it is a strong field ligand, it will be having the capacity to pair the unpaired electrons. So, when ammonia ligand comes, pairing occurs, and pairing occurs means this will be paired here, this will be paired here. So, 2 d orbitals, these two d orbitals will be empty when ammonia ligands approach, and 2 d orbitals available and rest of the s and p this is p, this is p, this is the p orbital, this is ns and np. Now, 2 d orbitals, s orbital and np orbitals are free. How many ligands are there? 6 ligands are there, 6 ammonia ligands are there. So, 6 hybrid orbitals should be provided by this cobalt atom. And now, 6 means 2 from the d orbitals already there, 1, 2, 3, 4, 5, 6. So, on total you can say that there is D2 sp3 hybridization, D2 sp3 hybridization. D2 means 2 from the D, 1 from the S and 3 from the P. So, totally 6 sp3 sorry D2 sp3 hybrid orbitals, and these D2 sp3 hybrid orbitals will be oriented towards the corners of an octahedron, and this ammonia molecule will be coming to form the cobalt ammonia coordinate bond. This is the formation of this complex. And while looking at the magnetic behavior of the complex, you can see that after forming the complex there are no unpaired electrons. So, the complex is diamagnetic. And now, another example is, again you have the same central metal atom cobalt with different ligand, that is COF6 3 minus. The structure is like this: cobalt at the center, all the 6 fluoride ions, they are acting as the ligands. And now again the oxidation state of cobalt is 3 plus, the same is the electronic configuration, that is 3d6, 3 electrons are gone, 2 from the 4s and 1 electron from the 3d, and after that you will get 3d6. And this fluoride ligands are very weak field ligands, very weak ligands. They can't actually pair the electrons. So, here pairing will not occur, and as a result what will happen? These electrons, how many d, like 1, 2, 3, 4, 5, 6 electrons, it will be like that only. The fluoride ions will not have the capacity to pair. So, these electrons will be remaining as such. Now, the metal is going for empty orbitals, and how many empty orbitals are to be provided? 6 empty orbitals are to be provided. So, how we can count 1, 2, 3, 4, 5, 6. It is sp3d2, sp3d2. 1 s orbital, 3 p orbital and 2 d orbital, but the d orbitals are outer d orbitals. It is not inner d orbitals because of the fluoride ligands are very weak. And now comment on the magnetic property of the complex. The complex is paramagnetic because we have 4 unpaired electrons. How many unpaired electrons? You can count actually. This is the case. Here it is electron. So, how many electrons are there? 1, 2, 3, 4. 4 unpaired electrons are in the complex. Complex is paramagnetic, and the mu value, this mu value, magnetic moment value, since there are 4 unpaired electrons, 4.9 or something Bohr magneton. That will be the magnetic moment of the complex. And now, see, we have discussed different complexes, and among them the 2 complexes were CONH3 6 times 3 plus and COF6 3 minus. Both are octahedral complexes. Both the complexes are octahedral, but one is diamagnetic, other is paramagnetic. We have the same central metal atom, right? Same central metal atom, that is cobalt is a central metal atom, but both are octahedral also, but one is diamagnetic, one is paramagnetic. The difference is due to the hybridization occurring here. One is sp3d2, other is d2sp3. In octahedral complexes, they may be outer orbital complexes and inner orbital complexes. Octahedral complexes may be outer orbital or inner orbital. Then what are outer orbital complexes? The complexes where outer d orbitals are used for hybridization are called as outer orbital complexes. In this case, in the sp3d2 means we are using this s, p and outer d, 2 d orbitals are taking part in the hybridization. So, that is why it is called as outer orbital complex. In this case, outer d orbitals are taking part in hybridization. And now, in the case of outer orbital complexes, maximum number of unpaired electrons will be present. You have seen that because there is no pairing, all the unpaired electrons will be there in the inner d orbitals. Since we are taking outer d orbitals, inner d orbitals will be containing the unpaired electrons. So, they will be paramagnetic in nature, and they will be most complexes will be paramagnetic, and they are also called as high spin complexes. It is very important. Complexes are high spin complex because maximum unpaired electrons are there, which that is why it is called as high spin complex. Examples are given: FeH2O 6 times 2 plus, COF6 3 minus, etc. are examples for outer orbital complex. The example given, they are all paramagnetic in nature, or they are called as high spin complexes. And now coming to the inner orbital complexes. Inner orbital complexes means in the hybridization the inner d orbitals will be taking part. So, the hybridization may be dsp2 or d2sp3. If the inner d orbitals are going for hybridization, they are called as inner d orbitals. And in those case you have, and those case you have when inner d orbitals are being used up, there will be pairing of electrons, that is it is achieved by pairing of electrons. There are no unpaired electrons present in the complex, and they are also called as low spin complexes, low spin or spin free or spin paired complexes. So, inner orbital complexes are also called as low spin, spin free or spin paired, and examples are chromium, that is CrCn 6 times 3 minus CrCO 6 times. These are all examples for inner orbital complexes. And now we can generalize that most of the D1, D2, D3 complexes are inner orbital complexes, that is the complexes with the electronic configuration D1, D2, D3. Most of the complexes with D1, D2, D3 are inner orbital complexes, and most of the D7 and D8 complexes, that is the complexes with electronic configuration D7 and D8 are outer orbital complexes. But D4, D5, D6 complexes will form both inner and outer orbital complexes. So, this is the way to summarize. D1, D2, D3 complexes will be most of the complexes will be forming inner orbital, and D7 and D8 will be outer orbital, but D4, D5, D6 will be forming both. And now coming to the merits of valence bond theory. This theory was the first one of the modern theory to explain the bonding in complexes. So, there are several merits for the theory, and number one is the maximum overlap proposed by valence bond theory could explain covalent bond in complexes. So, since this theory is emphasizing the overlapping nature of the metal and ligand orbitals. So, as a result it could explain the covalent bonding in complexes. And next is it could explain the geometry of complexes. What is the geometry? It could fairly well explain the geometry of complex. And now it could explain the diamagnetic and paramagnetic nature of complex. We have already discussed about that. And complexes are described as outer orbital and inner orbital in this, according to this theory. And it could explain the magnetic properties of the complexes also. And these are all the merits of valence bond theory. And the limitations of valence bond theory are, it did not give a quantitative interpretation of the magnetic data. Actually, I have told the value of this mu, but it was not given by valence bond theory. The value, the quantitative interpretation was not at all given by this theory. It fails to, it just told that yes, the complex is paramagnetic or this complex is diamagnetic. What is the quantity? What is the value of mu was not explained by this valence bond theory. And it also fails to explain various colors that the coordination compounds exhibit. So, the spectral property was not at all explained by valence bond theory. And also it does not give a quantitative interpretation of the thermodynamic stabilities of the coordination compounds, and also it does not also speak about the kinetic stabilities of these compounds as well. So, this theory fails to explain about the stability regarding thermodynamic or kinetic aspect. All those aspects could not be clearly distinguished or explained by this theory. And now another demerits are also there. Various predictions like that the valence bond theory makes regarding to the tetrahedral and square planar structures, that is 4 coordinated structures, are not completely accurate. According to valence bond theory, some complexes are forming square planar complexes, some others are forming tetrahedral complexes, and which all will form. What is the exact prediction could not be given. What is the reason for the formation of these square planar or tetrahedral complexes was not given by this theory. It does not draw any distinctive line between the weak and strong ligands. Some ligands are weak, some ligands are strong, some are capable of pairing the electrons, some are not capable, but it could not give a distinctive line for this kind of behavior. This was one of it was also a demerit of this theory. And this is all about the merits and demerits of this valence bond theory. And in this class, we have discussed the valence bond theory, its postulates, and based on this valence bond theory, we could explain the geometry of some complexes, hybridization, magnetic property, etc. And also the merits and demerits was discussed. And in the coming classes, we will be discussing about another most modern theories of coordination compounds like crystal field theory, molecular orbital theory, etc. And thanks for watching this video. Thank you.